It's my great pleasure to introduce the next speaker, who is a theoretical physicist from the University of Massachusetts and the founder of a field called quantum Bayesianism, Christopher Fuchs, who will speak on From Three Tenets of QBism to a Whitehead-style creative Pan-Experientialism. Let's please welcome Chris Fuchs.
I've watched several Olympics, and you always see the kids who are coming out to compete holding up their phones and doing selfies. And it just dawned on me, I'm giving a talk right after Roger Penrose. I should take a picture of the audience, because it's going to be a tough act to follow. That's yours. And this. No. There we go. So I gave my talk a rather fancy title, From Three Tenets of QBism to a Whitehead-style Pan-Creativism, but upon thinking about it, I decided that that's just too pompous. I should give it a more accurate title. The day QBism shot itself in the foot. It'll pretty much amount to the same thing. What I'd like to do today is give you an introduction to a point of view about quantum mechanics, or you might call it an interpretation, that we call QBism, and see where that leads ultimately in an ontological direction. So QBism took its start. We had been talking about it since about 1993. My PhD advisor, Carlton Caves, his postdoc, Rudiger Schock, and myself. And after mumbling for a number of years, we finally published a paper in 2002, the paper that you see, where we try to take the point of view that probabilities in quantum theory can be understood from a Bayesian point of view. In other words, not as infinite relative frequencies, not as objective chances, not as propensities, but something more along the Bayesian lines of thought. That was 2002. Not many people paid attention, or when they did pay attention, they threw tomatoes at us. A real turn happened in 2012 through 2014 when David Merman, who had been walking in the desert of quantum interpretations for much of his life, had an epiphany and said, "I believe QBism." And he started writing about it. When David Merman writes about something, a lot of people in the Quantum Foundations community pay attention. So since 2012, 2014, QBism has been taken seriously as one of the better-known interpretations of quantum theory. Where does QBism take its start? Well, it takes its start in a point of view that the late E.T. Jaynes, Edwin Jaynes, had. Jaynes was a supporter or a propounder of Bayesian probability theory in physics. He used it mostly for statistical physics. Jaynes wrote, "Our present quantum mechanical formalism is a peculiar mixture describing in part realities of nature, in part incomplete human information about nature, all scrambled up by Heisenberg and Bohr into an omelet that no one has seen how to unscramble. Yet we think that the unscrambling is a prerequisite for any further advance in physical theory. For if we cannot separate the subjective and objective aspects of the formalism, we cannot know what we are talking about. It is just that simple." So there's a rather novel idea here that one doesn't find in most interpretations. You don't see it in the many worlds interpretation. You don't see it in the objective collapse interpretations. You don't see it in Bohmian theory, as far as I can tell. And it is that the theory is a combination of two things. It's a combination of subjective and objective, and they've been mixed together. And a good source of the confusion has been that they're mixed together. So the task at hand is to try to pull them apart and put the objective on one side and try to understand that as a statement of what reality is, or what the quantum world is. The starting point for Jaynes was that different people, that's not working. Maybe it's not on. Oh well, we do it this way. Different people have different knowledge. So there's a state of reality represented by the dot there. Wonder if the tech guys can give me something that works. Oh, here's the problem. There's a state of reality represented by the dot, whereas two different people might have two different probability distributions for where the dot actually is. Are they at fault? Well, no, not necessarily. They have different states of knowledge. This is where they get two distributions for a single reality. We were able to do some amount of work with that idea as breaking the theory into two pieces, but in the end it just didn't go far enough. And the problem was that the idea of knowledge, if you think of knowledge as true justified belief, has a factive nature to it. If you think of knowledge, knowledge itself is a kind of combination of subjective and objective. I say I know something, you prove me wrong, well, then I didn't actually know it. There are conditions in the world that can prove knowledge wrong. But the word belief is a looser fitting thing to the world. So we started to turn from Jaynes's version of objective Bayesian probability theory to a kind of probability theory that is known as personalist or subjective. And this then led to a lot of progress that I'll try to show you a little of, and it gives us a corrective to Jaynes's program. What we find in the end is that some, in fact most elements of the formalism of quantum theory are in fact personalist or subjective, more subjective than Jaynes himself would ever go. Whereas some relations in the formalism are objective as one could want of a physical theory. Notice the distinction. Elements in the theory are subjective, but some relations in the theory are objective. And in order to be able to suss that out, you have to make the distinction between subjective and objective to begin with. So you want to look for a statement about reality? Well then, what this tells you, this methodology tells you, is to look for the statement about reality not in things like quantum states, but rather in the relations that one finds within the theory. So now let me give you a sense of what I mean by truly subjective probability. This is an idea that goes back to Bruno Definetti, and here's the way Dennis Lindley put the whole topic. The topic studied is the situation of an individual who is faced with uncertainty about some events of concern to him. All of us find ourselves in this position. Whenever we cross the road, we are in a situation of uncertainty. We might or might not survive crossing the road. Definetti's task is first to recognize openly the uncertainty surrounding us and then see how we can best understand it, how we can best moderate the uncertainty in our lives. The main result is that uncertainty can only be described satisfactorily in terms of probability theory. The coherentist paradigm, this coherentist paradigm is egocentric. It is the tale of a single person contemplating the world and not wanting to be stupid. He realizes that to do this, his statements of uncertainties must satisfy the laws of probability. So the idea is there's a primitive notion, uncertainty, and when we formalize the notion of uncertainty, the best way to formalize it ends up with the calculus of probability theory. To make this concrete, let me give this kind of definition of probability. Probabilities, in this point of view, correspond to the value of lottery tickets. Consider the lottery ticket that's worth $1 if an event E occurs. When a bookie writes down numbers like P of E or P of not E, P of E or F, etc., what he is saying is, this is a price I am willing to buy or sell that lottery ticket for. I'll either buy it for that price or I'll sell it for that price. And this now is what we take as a definition of probability. But this has no mathematical structure, so the word probability is empty at this point. It's just the price of a lottery ticket. The way you get structure is by adding something that I'll call a normative rule. The normative rule says the bookie should never declare numbers that will lead to a sure loss in one trial. Not in the long run, but in one trial. It turns out that this one simple rule leads to all the laws of probability theory. So if a bookie has written down this price for a lottery ticket that is worth $1 if E or F occurs, and he's written down these numbers for lottery tickets about if E occurs, if F occurs, and he hasn't adjusted his pricing scheme so that the two numbers equal each other, then a gambler can walk up to the table and say, I will buy some of these tickets, and I will sell some of these tickets at your price. And if he's done that correctly, in one trial, the bookie will have a sure loss. Why do I call this normative? Well, normative implies that there's a should somewhere in this story. What should be? Well, it should be that the numbers that are written down for the lottery tickets satisfy this relation. It's not a trivial thing to write these relations. Generally, when one makes probability assignment, one gets one's information from different sources. So maybe the bookie has written down this number by thinking about one source of information. And he's written down this number from another, and this number from another. And if the numbers don't mesh according to this equation, he's done something stupid. Probability theory doesn't tell you which of these is the correct assignment and which of these are the incorrect assignment. It's just a normative guide. It says to the bookie, you've done something stupid, you better readjust your numbers. How does he readjust his numbers? Well, he thinks harder, or he gathers more data, or he looks at a larger variety of sources. From this point of view, what do we mean by probability 1? Well, it means that one will buy or sell a lottery ticket worth $1 for, in fact, $1, full stop. That's all probability 1 means. It means somebody is willing to pay a full dollar for a lottery ticket that's worth $1. Particularly, it does not imply the truth of the proposition. If I write P of E equals 1, it doesn't mean that E is true. It doesn't say that if E is a physical property, P of E equals 1 means that E has the objective value of true. Here's the way the subjectivist Richard Jeffrey put it. The Bayesian framework replaces affirmation and denial by a continuum of judgmental probabilities in the interval 0, 1, endpoints included. Or what comes to the same thing, a continuum of judgmental odds in the interval 0 to infinity, endpoints included. Probability 1 corresponds to infinite odds. That's a reason for thinking in terms of odds, to remember how momentous it may be to assign probability 1 to a hypothesis. It means you would stake your all on it, but that doesn't mean it's true. Well, what does this have to do with physics in any shape or fashion? Well, let's think about the Einstein-Podolsky-Rosen criterion of reality. They say, of course, everyone probably in this audience knows they're thinking of a situation where they have two entangled particles, and Alice over here makes a measurement on one of them, and consequent to finding the outcome of her measurement, she's able to say what she would get at the other particle if she made the same measurement on it. So this is a situation that EPR were thinking, well, there's no superluminal signaling, so how can the particle on the right know that it should give the same answer as the particle on the left? So their criterion of reality was, if without in any way disturbing a system, one can gather the information required to predict with certainty, i.e. with probability equal to 1, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. The philosopher Tim Maudlin says of that statement, if I could make one change to the EPR paper in retrospect, it would be to alter the characterization of this criterion. The authors call it reasonable and in agreement with classical as well as quantum mechanical ideas of reality, but its status is actually much stronger than that. The criterion is, in the parlance of philosophers, analytic. That is, this criterion follows just from the very meanings of the words used in it. Now, Maudlin makes a big deal of that because then he says, this is the key thing that powers the following statement. What Bell proved and what theoretical physics has not yet properly absorbed is that the physical world is non-local. In other words, Einstein's wrong. There is spooky action at a distance, and it all hinges on this EPR criterion of reality. But most physicists are suspicious with this idea of non-locality because they ask, well, where does it stop? The experimentalist walks into his laboratory, he carefully calibrates his experiment, and he gets an outcome for a spin measurement. And those who believe in non-locality say, well, perhaps somebody sneezed in a faraway galaxy, and that's what led to your result. So physicists are suspicious of it. QBists are suspicious of it. And in particular, we're suspicious of this idea that it is an analytic statement, the EPR criterion. Well, it's just not so in QBism because it uses a different vocabulary. Probability in QBism is of the subjective Bayesian variety, and it doesn't have the same meanings that Mr. Maudlin says would lead to an analytic statement of that variety. So for QBism, the great lesson of John Bell, there is a lesson in John Bell. It's not that nature is non-local, it's that nature is creative. Even when I make a probability 1 ascription, it doesn't imply the pre-existence of the value I'll find. It means I'm very confident of it. It takes the action of measurement to bring the actual outcome about. Quantum measurement represents those moments of a kind of creation that are enacted or noticed by a quantum measure, an agent, a gambling agent. So more generally, let's think about quantum states. What do we do with quantum states? Well, we calculate probabilities from them. That's the ultimate use of a quantum state in any quantum mechanical calculation. But in the 70s, a new field arose called quantum information theory. And one thing we learned from quantum information theory is that if we consider a robust enough set of measurements, a set of measurements that are known as informationally complete, then the probabilities will uniquely specify a quantum state. So quantum states give rise to probabilities, but you could start the other way around and say probabilities give rise to this theoretical construction, quantum state. Well, if probabilities have to do with a tale of a single person not wanting to be stupid, then from this point of view, a quantum state is of the same character. Well, then, what about these quantum measuring devices or quantum preparation devices? Niels Bohr always drew them as big solid objects to represent the fact that they're sitting on the laboratory table and you can just look at them. Well, if you perform the same kind of analysis that you do with quantum states, use quantum information once more, then you can show that the specification of a measuring device corresponds to the specification of a set of conditional probabilities. And conditional probabilities being probabilities for a subjective Bayesian should be interpreted in the same way. So the description of a quantum measuring device, rather than being this solid kind of picture of a macroscopic entity, for QBism, these things are just as diaphanous as any probability assignment. They're not living on the table, they're living in an agent's thinking. This leads to tenet 1 of QBism. All probabilities, including all quantum probabilities, are so personal or subjective, they never tell nature what to do. This includes probability 1 assignments. Thus, quantum states, measurement operators, and unitary time evolution operators have no ontic hold on the world. They all represent personal judgments. So in the Janesian split, here's what we've managed to do. We've managed to put the various pieces of mathematics, quantum states, the permission operators that describe measurements, unitary time evolution operators, on this side of a pile. They correspond to the subjective. Now, the question is, what's left on the right-hand side? And before I start to tell you what's left, let me just ask, could it get worse? And, well, it does get worse, or better, depending upon your point of view, if you consider the scenario of Wigner's friend. This is a photograph of Eugene Wigner, and his friend is behind him. That's Edward Teller. And you'll notice that Wigner has his back to Teller. If he wants to make the best predictions that he can about what he will see when he turns around, he'll use the calculus of quantum mechanics. He'll effectively put Wigner in a box and say, that's a physical system behind me. On the other hand, I think we've learned from Copernicus that we really shouldn't privilege one of these gentlemen over the other. Wigner, on the inside of his box, feels experiences. For instance, maybe he's contemplating this light switch and what it will do if he flicks it. Well, if he flicks it, then you know, he'll either see a light come on or he won't. On the other hand, Wigner himself is using quantum theory to describe this, so he might be describing the whole situation unitarily. What gives? Is the Wigner point of view of getting outcomes correct, or is, the Wigner's friend point of view of getting his outcomes correct, or Wigner's where he uses the quantum mechanical formalism? Well, one can have one's cake and eat it too if you relativize the notion of a measurement outcome. This leads to tenet 2 of QBism. A quantum measurement is any action an agent takes upon the world, and its outcome just is the consequent personal experience this induces for the agent. Particularly, quantum measurement outcomes are not, to paraphrase Bohr, instances of irreversible amplification objectively recorded for everyone to see in advance, whose design is communicable in common language, suitably refined by the terminology of classical physics. This gives you a hint of why it's so difficult to read Bohr. So, Bohr had his heavy, solid measuring apparatuses. Quantum Bayesianism, QBism, has the experiences of the agent in their place. So this leads to this final picture, basically, of what QBism is about. It's about an agent immersed in the world and wanting to do his best not to be stupid with regard to how that world is structured. A measurement is, in this picture, an action that an agent takes on the external world. Taking the action on the external world leads to a consequent experience for the agent. The degrees of belief about what outcome he will get, what experience he will have, is summarized by this mathematical object. His degrees of belief about what he has done with these meters that are effectively part of his hand are characterized by these things, and unitary time evolutions also correspond to how he propagates one belief to another. When I first drew this diagram, one of my colleagues said it's like watching a quantum Bayesian shoot himself in the foot, because it seems to him that we've given up on all relation between quantum theory and reality. But notice that quantum theory can be used by anyone in this picture. I focused on one agent, but there are agents all over the world who are using quantum mechanics. Those other users, for the agent in focus, are just physical systems like anything else. And each of those individual agents are using the Born rule. So that tells you that the Born rule has an objective character to it. It's a feature of quantum theory that any agent can adopt. And just like in the general rules of probability theory, the rule is normative. And so when we wrote P of E or F equals P of E plus P of F, we thought of that in a normative sense. Now that we've recognize that quantum states and measurement operators are ascriptions of probability, then one can say, well, this says that the probabilities on the left must be adjusted to be in alignment with the various probability statements on the right. That's tenet 3 of QBism. The Born rule, the foundation of what quantum theory means for QBism, is a normative statement. It's an empirical addition to the coherentist paradigm, and consequently about the decision-making behavior any individual agent should strive for. It's not a descriptive law of nature in the usual sense, say the usual sense of general relativity, where a law of nature tells space-time exactly what to do. The Born rule is not like that. It doesn't tell nature what to do. It tells the agent how best to gamble. But we do want more reality. If you want more reality, then the question becomes, why this particular rule? Why this normative rule? What conditions of the world make this the right rule to use? And that's where the real work of QBism kicks in. This is a general lecture. If I told you about the details of QBism, I would bore you stiff because they become quite mathematical quite quickly. But what's at stake is trying to understand the Born rule as this normative rule in as clear and as possible. With the right kind of mathematics, again from quantum information theory, one can rewrite the Born rule to get rid of the mathematical objects of quantum states and measurement operators and end up with an expression that's purely about probabilities. Well, maybe you want more reality than that already. That's telling us something about reality, but what is it telling us? Here's what I think it is telling us. When we drew this diagram and said that quantum measurements represent those moments of creation that are enacted or noticed, notice that quantum states are not directly about the things that are happening in the world, and measurement operators are not about the things happening in the world, and so on. In this picture, the only thing happening is this little spark that flies between the external world and the internal world of the agent. Here's the way Wolfgang Pauli put it, and I have just a couple more slides. I'm more and more expecting a further revolutionizing of the basic concepts of physics in connection with this, particularly the manner in which the space-time continuum is currently introduced into it appears to me to be increasingly unsatisfactory. Something only really happens when an observation is being made. Between the observations, nothing at all happens. Only time has, in the interval, irreversibly progressed on the mathematical papers. This suggests, actually, that the notion of something happening, the little spark, is exactly what we would like to abstract. William James said it nicely. Here I take the bull by the horns and ask, why not? Our acts, our turning places, where we seem to make ourselves and grow, are the parts of the world closest to which we, or the parts of the world to which we are closest, the parts of which our knowledge is the most intimate and complete. Why should we not take them at their face value? Why may not the actual turning places and growing places, which they seem to be, of the world, why not the workshop of being where we catch fact in the making? Fact in the making is the key idea. This suggests that what QBism is aiming for is to abstract this little element that we find in the theory, always focused on the quantum measuring process, and say, this is what the world is made of. They're events of a sort, but ostensibly they all have a polarity, like Whitehead's throbs of experience. You look at the diagram, it's not immediately obvious, but it can be decomposed into an objective end and a subjective end. So I think Whitehead was onto something, and I think QBism is a methodology for going in that direction. But Whitehead, per se, cannot be exactly right. Whitehead wasn't involved in modern physics, despite what some historians might think. His knowledge of quantum theory wasn't very deep. His vision, his ontology, was not tempered by the deep details of quantum theory. To ask why the Born rule is to construct a detailed picture of the characteristics of these actual occasions in Whitehead's terminology, or throbs of experience. If we understand their characteristics, then we will understand why we should adopt the normative rule that we do, and you can reverse engineer. Why do we have the normative rule that we do? that tells us something about the characteristics of these events that are occurring in nature. But it's a long road. QBism is a project, and there's still a lot of work to do. Thank you.